Welcome everyone. In this video I would like to talk about a real case study about the calculation of the PCI. The calculation of the PCI contributes in the decision-making process regarding the maintenance and rehabilitation techniques. For example, according to the ASTM, if the pavement is in excellent condition, as you can see here just after construction, we will do nothing regarding the maintenance and rehabilitation. If small cracks started to appear, the pavement is said to be in good condition. We will apply the routine maintenance. If the number of cracks increased, as you can see here, the pavement is in fair condition and we will apply the preventative maintenance. If the width of these cracks started to increase, the pavement is said to be in poor condition and it requires structural improvement. If the number of cracks started to increase and propagates through the whole pavement, and there are a lot of patches as you can see here, the pavement is in failed condition and it requires base rehabilitation. As you can see, this map is for the United States. It was a study that ranks the state highway systems by road conditions, safety, and cost effectiveness, which contributes to the decision making regarding the maintenance and rehabilitation, and also provides infrastructure update about the existing pavement. So we will start by the PCI definition and rating scale. We will talk about the road inspection in ArcGIS and how to determine the type of pavement and width of road. We will divide our road into a number of segments based on the intersections of other streets with the studded road. We will determine the distress types, their quantities and severity levels. Then we will digitize these distresses in ArcGIS. We will calculate the PCI depending on the available distresses types, quantities and severity levels for flexible and rigid pavements. Then we will talk about the digitization of the PCI on the road based on each road segment. Finally, we will introduce the calculation of PCI using Micro PAVER program. Then we will talk about Micro PAVER and GIS integration. As we said previously, pavement condition index is a numerical scale of the pavement condition that ranges from 0, which means that the pavement has failed, to 100, which means the pavement is in its perfect condition just after construction. And the PCI contributes in the decision-making process depending on the PCI. For example, if your PCI is between 71 and 100, you will apply the preventive maintenance techniques. If it's between 41 and 70, it means your road requires major rehabilitation. And from 0 to 40, it means your road requires reconstruction from the base level. The aim of the road inspection in ArcGIS is to determine the pavement types, the length of each pavement, and road width variation. For example, here, this is a rigid pavement, Portland cement concrete slabs. As you can see here, we have transverse joints and longitudinal joints. Here we have 2 lanes in each direction. Here in the flexible pavement, we do not have those transverse or longitudinal joints. We have here a railroad crossing and some cracks that are associated with the flexible pavement, like this linear crack, some patches, and some weathering and raveling of aggregates. So the aim of road inspection is to determine the pavement types, the length of each pavement, and road width. Our road has a length of approximately 3.6 miles. It was divided into several sections of flexible and rigid pavements. The rigid pavement after inspection was 1.127 miles and the flexible pavements was 2.47 miles. The road width varied between 14.4 and 42.75 feet. It was divided into several number of sections based on the pavement type and road width, because each section will have its own PCI samples and its own calculation of cracks and digitization. It is important to say that the PCI was calculated for the whole road and not per direction as per the client's orders. For example, here the first section had a width of 385 feet. The width of the road was 14.4 feet. The next section, the length was 5,570 feet, and the width of the road was 42.75 feet. The pavement type here was rigid pavement. After that, it was flexible pavement till the end. For example, here the first section in the flexible pavement was 11,480 feet, and the pavement width was 40 feet. And these 6 sections represent the number of sections along the road. We have here 2 rigid pavement sections and 4 flexible pavement sections. It should also be noted that we must not combine the PCI of rigid and flexible pavement. We should separate between them while the calculation of the PCI, since the cost of maintenance and rehabilitation in both pavements is totally different, and you will have false PCI judgment of the road if you combine the flexible and rigid pavements together. Now let's talk in details about these samples. The first section, it was a rigid pavement. The recommended number of slabs in one sample is 20 plus or minus 8 slabs. So we are talking about 12 slabs to 28 slabs per sample, and it is recommended by the ASTM to choose the number of slabs to be 20. The road length or section length in this case was 385 feet. The slab length was 11.25 feet. The width of the slab is equal to the width of the road, which was 14.4 feet. The total number of slabs in this section was 34.22 slabs. Samples, I'm sorry. How did we obtain this number? It is equal to 385 divided by 11.25, and it was approximated to 34. The allowable number of error recommended by the ASTM is equal to 5. The standard deviation of the PCI between sample units was 15 for a PCI range of 35, which means that the difference between the maximum PCI and the minimum PCI in this section should not exceed 35, and if it exceeded 35, we should increase the number of samples to be studied. So the minimum number of samples to be studied here is equal to 17.73. It was calculated from this equation given by the ASTM. It was approximated to 18 slabs. And the sampling interval is equal to n capital over n small, was equal to 1.889 approximated to 1, which means that all samples should be studied. The second section in the rigid pavement, section B, the road length was 5,570 feet. the road width was 42.75 feet. This is the road width, and this is the sample length, and I chose the number of slabs in one sample to be 20. The sample length was 100, so this number here is 100, and the width is 42.75. These are the length and the width of our sample. And also the number of slabs in one sample, as I said, was 20. The total number of samples in this road would be equal to 5,570, the road length divided by the sample length, which means that we have 55.7 samples to be studied, approximated to 56 samples. And also the allowable error and standard deviation are equal to 5 and 15 respectively. The minimum number of samples to be studied was calculated also from this equation. It was 22.1, which is 22 minimum number of samples to be studied. The sampling interval is equal to n capital over n small is equal to 2.54, rounded down to 2, which means that I will start by the first sample or the second sample, and the next studied sample is equal to the start plus I, which is 2, and the next sample to be studied is S plus 2I. Flexible pavement, section A, the first section in flexible pavement. The road length was 11,480 feet, and this is the road width. This is the road width, which is 40, and the sample length was 62.5. Since the sample area required by the ASTM is taken as 2,500 feet square as the average sample area, we are free to choose the sample area between 1,500 to 3,500. However, it is recommended to use the mean value, which is 2,500 feet square. The total number of samples calculated was 183.6, approximated to 184. The allowable error and standard deviation recommended for flexible pavement are 5 and 10 respectively. The minimum number of samples calculated using this equation was 14.79, approximated to 15. So we will study only 15 samples that will represent the behavior of 184 samples. The sampling interval calculated was equal to 12. So we are free to start our inspection between the first sample and the 12th sample. This will be S, and the next sample to be studied will be equal to S plus I, which is 12. After that, S plus 2I, and so on. A similar approach was used in the other flexible pavement sections. As you can see here, flexible pavement section D, the road length was 705. This is the road width, and the sample area was set to 2,000 feet square. And these are the calculations of the total number of samples, allowable error, standard deviation, minimum number of samples, and so on. And also a similar approach was used for the other flexible pavement sections, as you can see here, section B and section C. After dividing the road into a number of sections depending on the pavement type and the road width, and calculation the number of samples to be inspected, now comes a very important task, which is the determination of these stresses, types, quantities, and severity levels. These stresses are the cracks that appear on the road. Some of these cracks are measured in linear feet, others are measured in the feet square as an area, and others are measured as a count, like potholes, for example. And the severity level is determined by the ASTM depending on the severity of this crack and the width of the crack, the depth of the crack, and the area of these cracks. For example, here, if we are talking about rigid pavement, this sample here consists of 20 slabs. We might see here some high severity punch outs and also high severity lane or shoulder drop off. We might see some spooling joints. Here we also have lane or shoulder drop off. We might see also some polished aggregates. We also can see here a linear crack. If we are talking about flexible pavements, as you can see in both images, this is a high severity railroad crossing measured by area. We can see here some linear cracks and also a lot of patching, which seems to be in very bad condition. Here we might see a lot of linear cracks of medium severity, and this patching here, it looks somehow new, so it might be a low severity patching. We also have some weathering or raveling of aggregates. So for example here, for linear cracks, this is measured by feet, and the severity is determined by the width of this crack. For patching, the severity level is determined by the visual inspection and the age of the patch, and the quantity is measured in feet square. The same applies for the railroad crossing. It is measured in feet square. The punch outs are measured in linear feet. Their severity depends on the width of this punch out. The lane or shoulder drop off is measured also by linear feet, and the severity by the depth of the drop or the shoulder of the road. The same applies for spooling joints. And finally, the polished aggregates are measured by feet square as an area. So digitization of these stresses in ArcGIS means that we create polygons and lines over these stresses and cracks that are available in our sample. For example, here in the rigid pavement, this punch out is a polygon, rectangular polygon in red, and red means that it has a high severity depending on the ASTM. Some distresses are measured in linear feet, others are measured in areas, and others are measured in count, such as potholes. For example, here linear cracks, that was a medium severity linear crack, and this area here drawn in green, that was a low severity, because green is low severity, that was low severity polished aggregates. If we want to look about the distresses in the flexible pavement, here we have a high severity railroad crossing, and that is measured in area. We also have here a high severity linear crack. We have an area of weathering or raveling, and we have also a lot of patches with a high severity. Now, after the inspection and the determination of each distress and distress severity, and quantity, we need to calculate the pavement condition index for flexible and rigid pavements. This is a typical calculation sheet for asphalt surface roads. Here we are given the 19 distresses defined by the ASTM. Here you draw your sample size, that was 25 feet multiplies 100 feet, which means that the area is 2500 square feet. And here you start to write down your distresses. For example, 1L means that you have alligator cracking, and L stands for low severity. So the quantity, how much alligator cracking with low severity do we have in our sample, which has an area of 2500 square feet. We have 1 multiplies 5 and 1 multiplies 4 and 1 multiplies 4. So the total is 5 plus 4 plus 4, which gives us 13. And the density as a percentage is 13, the total divided by the area of this sample, which is 2500 square feet multiplies 100, gives us 0.52%. Now to determine the deduct value, here for the alligator cracking, this graph is also provided by the ASTM. On the x-axis we have the distress density as a percent. We have 0.52, here is 0.1, 0.2, 0.3, 0.4, 0.5, and we have low severity. We have three curves, low, medium, and high severity. Our curve is this one, since we have low severity. If we go up there till we intersect with the low severity curve and read the value on the y-axis, you will get around 7.9. And the same methodology is applied for other distresses, where each distress has its own curve. So here we have alligator cracking and we also have edge cracking. So we have 19 curves for all those distresses, and each distress is defined by 3 severity levels: high and medium and low. We have a similar asphalt surface road and parking lots. This table here represents asphalt surface roads and parking lots. We have a similar sheet for rigid pavements. However, we do not have here the sample area. However, we have the number of slabs, and I will make a separate video for the rigid pavement. Now, after calculating the deduct values for all the distresses, the next step to calculate the PCI is to arrange those deduct values in descending order. As you can see here, arrangement is in descending order, and the last deduct value is multiplied by 0.9. Here 0.9 multiplies 5.3 will gives us 4.8. So why did we do that? We did that because we calculated the maximum allowable number of deducts for our sample. The maximum allowable number of deducts is represented by m. M is equal to 1 plus 9 over 98 multiplies 100 minus the highest deduct value. As you can see here, it is equal to 7.9, and 7.9 is less than 8, and 8 is our deduct values count. We have 8 deduct values. Since m is less than the number of deducts, then the deduct number 8 will be multiplied by the remainder of 7.9, which means that 5.3 multiplies 0.9, the remainder will give us 4.8, here this value. So what if m is more than the number of deducts? We will use all the number of deducts without any correction or without any multiplication. As you can see here, if less than m deduct values are available, all of the deduct values are used. Now, after arranging the deduct values in descending order, we calculate the total. Actually, sum up all those values will give us 104.7, and the Q here, this Q, is the number of deduct values more than 2, because it is a surfaced road. So how many numbers here in this first row are more than 2? We have all the numbers are more than 2, and their count is 8. So here we have the total deduct value on the x-axis and the corrected deduct value on the y-axis, and that is our aim. Here we have 104.7, and this curve here, we do not have a curve for 8. You can imagine that you have a curve for 8 here intersecting the Q equal to 7, and then you calculate the corrected deduct value as 51. So in the next iteration, the first deduct value that is more than 2 will be equal to 2. So here 4.8 is the first or the smallest deduct value more than 2 will be 2 in the next iteration, and then we will have 7 deduct values more than 2, and then we calculate the total and then the corrected deduct value again, and then we keep iterating every time the first deduct value more than 2 will be equal to 2. Here Q is equal to 5 because we have 5 numbers more than 2, and so on until Q is equal to 1. At this value we will stop our iterations, and the PCI for this sample is equal to 100 minus the maximum corrected deduct value. So the maximum corrected deduct value here is 51. That was the first value. 100 minus 51 is equal to 49, and that is our PCI for this sample. Similar procedures are used in the rigid pavement, and I will provide an example for rigid pavements in the next videos. Calculating the pavement condition index for sections. Now this is very important if you want to calculate the pavement condition index for a road. For example, the road name is A Street. That is an imaginary road, and this road intersects with several roads, as you can see here, road 1 and road 2 and road 3. And let's say, for example, this road A Street has different pavement types. For example, this section here is rigid pavement, and this one is flexible, and this one is rigid, and so on. And this road also has different width, so the width of rigid pavement section is different from this flexible pavement section, and also is different from this rigid pavement section, and so on. So you need to have different PCI sections along this road. So we will have a section here for the samples in the rigid pavement section, and another section here in the flexible pavement, and another one in the rigid pavement, and so on. So the rigid pavement will be divided, this section will be divided into number of samples, and this flexible pavement also will be divided into number of samples. The same applies for this rigid pavement section. For example, you will study here the first sample and the last one. In the flexible pavement section, you will study the first, the third, the fifth, In this section you will study the first, the third, and the fifth. And now we need to present your PCI for this road. Now it is not possible to combine the rigid pavement PCI and the flexible pavement PCI because the cost of maintenance and rehabilitation techniques, which is the conclusion of the PCI, is not similar for both types of pavements. So combining or taking an average PCI for this section here is not applicable at all. You will have to provide a PCI value for this section here between, let's say, road 0 and road 1. You will have a PCI value. How will you calculate this PCI? You already calculated the PCI for the first sample and the last one, and they are homogeneous, which means that they have the same pavement type and the same road width. So the PCI here is PCI 1 plus 5 over 2, simply taking the average. For this section between road 1 and road 2, you already calculated the PCI for the first sample, the third, the fifth. So you will calculate the PCI average here is equal to PCI 1 plus 3 plus 5 divided by their count 3, and the same applies for this section between road 2 and road 3. So whenever we have different pavement types and different road widths, we need to calculate different PCI values along the section of the road. So determination of section PCI. As I said previously in the previous slide, if all surveyed sample units are equal in size, the section PCI is the average of the sample unit PCI and also the pavement type. So what if the sample units are not equal in size? If all surveyed sample units are not equal in size, then the PCI of the section, or PCI-S, is calculated as the area weighted PCI of the surveyed sample units, or PCI-R, using the following equation. So the PCI of the section is equal to PCI of the surveyed sample units, which is equal to the summation of PCI of the individual sample units multiplies the area of each sample unit divided by the summation of their areas. However, on that condition, they must have the same pavement type. So basically, what is written here, if you have, for example, a section with width, let's say 30 feet, and another section, the width became 15 feet. Here you will have sample size different from the sample size here, but you have the same pavement type, let's say flexible pavement. So you can calculate a PCI value which describes both roads and both widths by applying into this equation. So this equation is only applicable if you have the same pavement type, however different areas. Now let's see how to calculate the PCI for sections for a given road, and this is a real case study done in the United States. Let's draw our sections. For example, here these are our sections, and this is road A Street. The intersections with A Street are 1, 2, 3, 4, 5, 6, and 7. From street 1 to street 4, these are flexible pavement, and from street 5, between 4 and 5, 6 and 7, these are rigid pavements. As you can see here, flexible pavement and rigid pavement. So between 1 and 2, we had 2 samples to be studied. Now I'm talking about n small and not n capital. N small is the minimum number of samples to be studied. We had only 2 samples to be studied in this case, and the first sample PCI was 62, the second one was 76, which means that the average PCI of the section 1, 2, from street 1 to street 2 on street A street is 69, and according to the ASTM color code, 69 is a fair condition. Now let's take another example between streets 2 and 3. We had 4 samples to be inspected, and their average was 61, and 61 is also fair. Between 3 and 4, we had 5 samples to be studied. In this region here, we had 5 samples, and their average was 52, and 52 is poor condition, and so on. The same applies for other sections. That is how to calculate or present the PCI for a road intersecting different streets. Digitization of the PCI on the road based on each segment. As I said in the previous slide, we calculated the PCI and provided a color code for this road. This is our A street, and there is a color code here for each section. So this road here was divided into number of sections depending on the intersections between the streets in the reality and the intersections with our road A street. And when you digitize in the ArcGIS, I provided a color code based on the ASTM for every PCI rating scale. We have satisfactory in green, fair in yellow, poor in red, green is satisfactory also, and the dark red is very poor condition. And each color represents the PCI between the defined road segments or intersections. Now the previously discussed method to calculate the PCI provided by the big table, and you start to write down your distresses and so on and prepare this big table. This is really time consuming procedure to calculate the PCI, because after you finish this table you have to go into another table where you descendingly arrange your deduct values, then calculate the total, the Q, and the corrected deduct value from other tables, and you start to read the distresses and so on until you calculate the PCI. So there is another method to calculate the PCI using the program known as Micro PAVER that is developed by the US Army Corps of Engineers. Here in this program you will enter the section width, section length, the surface type, Portland cement concrete in this case, that is a roadway, and the section area is automatically calculated. You also enter the inspection date, and here the first sample that you are going to inspect, you choose it, and the sample unit size is 20 slabs per sample, and then you start to choose your distress type and select the severity and enter the quantity. and then you click on add distress. After you add this distress, automatically you will get the sample number 2 and also start to type your distresses that you saw in this slab or sample during the visual inspection. When you enter all the slabs that you are going to inspect, you click on calculate conditions. After you click on calculate conditions, you will get here the branch name or the street name, the section length, section area, and section width, and you will also get a condition, the PCI value as an average for all those inspected samples. For example, here it was 70 given by the yellow number, and here clicking on the condition indices, you have sample number 1 with all its distresses, then sample number 2, and the severity level is written beside each distress type and its quantity. If you click on sample conditions, you will get the PCI per sample. For example, here that was sample number 1, sample number 2, sample number 3, sample number 4, and sample number 5. Here we surveyed 55 samples and we had 55 PCIs. Their average is 70. Finally, integration between Micro PAVER program and GIS. It is very useful, especially if you are working on infrastructure projects in the road sector and you need to calculate the PCI for a given network or a given road. There is a very important tool in the Micro PAVER program which allows for integration between the Micro PAVER and GIS, where the PAVER output, which is the PCI, is transferred to GIS as a shapefile to be displayed instantly on the map. This is known as condition analysis, where the condition analysis feature allows users to view the condition of the entire pavement network or any specified subset of the network. If we're talking about a road, this feature reports past conditions based on prior interpolated values between previous inspections. It reports projected conditions based on prediction models. In PAVER 5.2, our edition, however, right now there is another edition 6.2.5. It also has this condition analysis. In PAVER 5.2, condition can be viewed on GIS maps in addition to tables, graphs, as you can see here in figure 5. You can internally view these maps on Micro PAVER, or we can export it as a shapefile on the GIS. That is very useful, especially if you want to take a decision regarding the maintenance or rehabilitation of a network or a specific cross-section, depending on the PCI value of this network or this road. Thank you so much for listening to our video. I hope you enjoyed it, and there are also very useful PDFs in the description of this video which helps you to calculate the PCI integration between GIS and Micro PAVER and a lot more. If you have any questions or any suggestions or inquiries, please contact me on my email. Thank you.